So let us start with the next preparation of carboxylic acids from Grignard reagents. Now here we find that Grignard reagents, these are given as RMGX, where X stands for halogens, and R here is a very special R, so that's very important to know that this R here is partially negative, and so we may say that this is like nucleophilic center, right? So it is an excellent nucleophilic center. That is what we understand. Now, in order to get a carboxylic acid, we will have to allow Grignard reagent to react with carbon dioxide. So what we generally do is we take ethereal solution. Grignard reagent generally is prepared in solvents like ether, and ethereal solution of RMGX is poured over, is added to dry ice. This gives us an adduct which, upon acidification, gives us corresponding carboxylic acids. So this is a summary of what we have to do, right? So we take ethereal solution, and just a moment. All right. So now let me show you how it goes. So we take any Grignard reagent like RMGX and we allow it to react with carbon dioxide. Carbon dioxide has a reasonably positive carbon, and therefore there is this nucleophilic R getting added onto carbon of carbon dioxide, and pi bond collapses onto oxygen, and finally what we get is R, C double bond O, O minus, and MgX plus. This is the adduct that you get, and this upon acidification would give you R, C double bond O, and OH. This is your carboxylic acid. So this is Grignard added onto dry ice, and this is your carboxylic acid. So it is a pretty simple reaction, not at all very difficult, and you can very easily all right, what we can do is we can put it as a separate reaction. So I think you've understood this, not a very difficult thing to do. I could have given you individual examples. If you want an individual example, I can put up one individual example, like specific. We can start with CH3 MgBr, and we can react it with carbon dioxide, dry ice. The CH3, the negative dipole, attacks the carbon, pi bond collapses, and finally we get CH3, C double bond O, O minus, MgBr plus, and this upon acidification, so let us put H plus and water, and we get CH3, C double bond O, and OH. So this is pretty simple and not at all difficult. I took a specific example. You can also take up this specific example, and this is how it goes, right? So we've done the fifth preparative method. This is from Grignard reagent, right? Now we move on to the next preparation, preparation number 6, which is based on hydrolysis once again. Okay, let us start with the next preparation. Preparation of carboxylic acids from esters, acid anhydrides, and acid halides. Now let us understand how this goes. First of all, you have to know that an acid halide would be like an acid chloride, and it generally has this form RC double bond O and Cl, right? Generally we take acid chlorides. Now here you can see that there is this leaving group here, chlorine. If you look at this, this is an anhydride, and you can see that it also has a leaving group here, right? We can put R dash if you want, so that you exactly know, right? And you also have an ester, RC double bond O and OR dash. Now here, once again, you have a leaving group here once again. So these are all different leaving groups which you have to know. Sorry. So these are all different leaving groups. And the rate of the reactions, right, would depend on how good a leaving group is. Now, if you have attended my lectures for halogens, you already know that leaving groups or strength of any group to leave, right, or how good a leaving group is would depend on its basicity, right? It would depend on its basicity, and I have already given you the full thing, right? Weaker a base, better a leaving group it is, right? So basicity, a weaker base would be a better leaving group. That is how it is, right? So all that you will have to know, but very quickly I'm going to show you how this works, right? So let us take up the hydrolysis part of how acid chloride can be converted into a carboxylic acid. So let us start here. RC double bond O and Cl is treated with water. Water has oxygen, which is the nucleophilic center. And the first thing that happens is the pi bond collapses onto oxygen with a nucleophilic attack of oxygen onto that positive carbon. And we have this. Now your leaving group comes into play, and this is your H2O plus. Now this happens, right? Once again the pi bond gets formed, and you have RC double bond O, OH2 plus Cl minus. Now Cl minus is going to act as a base and would try to pull out one of the hydrogens, and you will have RC double bond O and OH minus HCl. So this is how it goes, and this is the first preparative method that you have, right? I can group this up, and you can have a clear idea about how this goes, right? So leaving group plays a very important role in deciding the rate of reaction. So here, as this chlorine leaves, right, you can realize that if this is a good leaving group, then the rate of reaction would be more. So rate of such reactions would depend directly on the ability of a group to leave, right? I would be talking about that more after I show you these reactions. Right, so this is one thing. Now many a times, this reaction is quite good with acid chlorides, so I think you don't have to worry about how a group leaves. This reaction is reasonably good, right? And you know that if you use, instead of water, if you use NaOH, for example, then the same reaction can very easily proceed like this. So using NaOH, you have aqueous NaOH, you have this. So the reaction is much faster because OH minus is much better nucleophile as compared to water. Having negative charge on it, the rate of reaction is extremely good. And you have this. The same thing that happens, right? Now it is all about this moving in and this moving out. So you have RC double bond O and OH plus Cl minus. Obviously, in basic conditions, RC double O H would become RCOO minus. So this carboxylic acid would actually remain in form of RCOO and not RCOOH. But that's okay. I just wanted to show you how the reaction goes with NaOH. With NaOH, the rate of reaction is faster. You have to know that. All right. Let me take up one more reaction. Now I'm going to take up the reaction of acid anhydride. Now acid anhydride also has got a leaving group, right? But yeah, let me tell you one more thing, that when you talk about acid halide, you have to know that this is RC double bond O, and then we have this C double bond O and R dash. Now whichever carbon is more positive, that is where the attack happens. So you also have to know where would water attack, this carbon or this carbon, depending on which carbon is more positive, and that depends on R group. Electron withdrawing groups here would make this carbon more positive, and this would be attacked first. If there are more electron withdrawing groups here, then this would be attacked. So it depends, right? You have to consider inductive effect here for assessing where the reaction would take place. However, here let us consider any one option. So we're not very fussy about that. Let us consider that the reaction is going to happen on this carbonyl group here, because we have decided that this is our leaving group, right? So we've considered this. We've considered this as our leaving group, right? So this is our leaving group. And therefore now we put it like this, RCO minus, you have OCOR dash, I'm putting all the leaving group together, and you have OH2 plus. Now comes, now this is going to come back, leaving group leaves, and you can see that it goes like this, RC double bond O, and then you have this O, H, H, and plus. Now this would further, your RCOO minus or R dash C double O minus is going to pull one H here, and finally we get R COOH plus R dash COOH, right? So this is how the reaction goes. This is with anhydrides, how water would react or how hydrolysis would take place. Let me tell you one very important thing, that with anhydrides, the rate of reaction is slow, right? Which also proves that OCOR is not as good a leaving group as Cl minus. So rate of reaction is slow. So if you take cold water for doing this reaction, the rate of reaction is less and slow. However, if you take up hot water or boiling water, the rate of reaction is faster. So as leaving group becomes poorer, right, the rate of reaction also slows down, right? Now, what makes this group a poorer leaving group as compared to Cl, I would talk about that. Just wait for a while. Let me take up one more reaction, and this is the reaction of hydrolysis of ester. Once again, I hope now you must have realized what mechanism we have. Now with ester, the rate of reaction is slightly slow, and so we either have to use mineral acids or we may have to use alkalis, any one. I would tell you what exactly happens in each case, right? So if I use H plus, right, there is protonation taking place. So catalytic amount of H plus, you will have protonation taking place here, and it would convert this OH, and this would become plus and OR dash. Now with this, there is this resonating form generated, and in this resonating form you find that your carbon has become positive. Now with this positive carbon, right, the attack of water is quite fast. So now your water is going to attack very fast, right? And you may have RCOH OR dash, and then we have this OH and H and plus. Now you can have internal proton transfer, so you can have H plus transfer taking place, wherein you find that OR dash gets converted into a good leaving group by protonating itself. So you have this, OR and then H. So let me put it like this: OR dash and H plus, and then there is this OH. Now you may have lone pair coming in and this moving out, which gives you RCOH and double bond O H plus, and this is minus R dash OH. Now let me put it properly. And now we can have our and now there is loss of proton to the solvent, and we have our acid generated, right? So that is how we get our acid. So minus H plus, deprotonation, proton is generally lost to the solvent. This is your carboxylic acid, right? So I think this was pretty okay with your, or else let me put this all together. Yeah. So this is this was ester undergoing hydrolysis under acidic conditions. Alkaline conditions, if you want to know how this happens, I think it is again the same thing. If you take OR dash, which is a leaving group, and with OH minus, there would be a simple attack on this. Pi bond collapses. You have R, C, O minus, OR dash, and OH. This would remove OR, and you have your R, C double bond O, OH plus OR dash minus. Now there would be a proton transfer because the medium is basic. You have R, C double bond O, O minus plus R dash OH. Thus, in alkaline medium, this is pretty easy, right? You can have your ester undergoing, a simple basic hydrolysis. I think things are very simple here, right? All right, after having done all this, I'm going to talk about the strength of leaving group, and in such reactions, which of the three components would react faster. Let us take up that. So just remember one thing, the leaving capacity of any group is inversely related to its basicity. Now let us take up Cl as a leaving group, right? Cl minus as a leaving group. Now its conjugate, you have to take its conjugate acid. So conjugate acid would be HCl, which is, a strong acid. The other leaving group that we took up was OCOR dash. The conjugate acid would be RCOOH, organic acid. And the other one was OR dash minus, and its conjugate acid here is R dash OH. Now, if you look at the strength, the acidic strength now follows HCl greater than R dash C double OH greater than R dash OH. Therefore, strength of conjugate base, you know the basics, right? When acid is strong, its base, conjugate base would be weak. So Cl minus is weaker than R dash C double O minus, which is weaker than R dash O minus. That makes R dash O as the strongest base. Now, therefore, leaving capacity is inversely related. So once again, the one which is the weakest base is the best leaving group. So Cl minus, R dash C double O minus. Thus, it is very easy to understand that Cl minus being the best leaving group, the rate of reaction with acid chloride is the fastest. R dash C double O comes second. So that's the leaving group you find in anhydrides. So in anhydrides, the leaving capacity is slightly less as compared to acid chlorides, and therefore the rate of reaction of anhydrides here is lesser than acid chlorides. And R dash O is the strongest base amongst all of them, and therefore it has the worst leaving capacity, and therefore you find that the rate of reaction with esters is the minimal, right, amongst these three. Right. So I hope you've understood how this goes. For the full list of leaving capacities of different groups, you can check my notes, or else you can go through the notes given in given for halogens. I think halogen containing compounds, I have given a list of leaving capacities of different groups. Check that out. Okay. Any doubts you can always ask in the regular lectures. Okay. Yeah, so let us come to the next method of preparing carboxylic acids. This is a reaction called Koch reaction, and generally used on an industrial scale. They say that monocarboxylic acids, they can be prepared by reaction with carbon monoxide and steam, right? They can be prepared from carbon monoxide and steam. The conditions would be like, temperature needed for this would be somewhere around 573 to 673 kelvins, and there's also pressure. So reaction is done under pressure, right? And you can have monocarboxylic acids produced, right? So, and the reaction takes place from olefins. So olefins, which are alkenes, and olefins can be treated with this, right? And this would give you monocarboxylic acids. So this is how the reaction is done. Let me give you some specific examples. Now, if you start with CH2 double bond CH2, one of the common alkenes, and you allow it to react with carbon monoxide and H2O, this is normally taken in form of steam. And here the conditions would be, 573 to 673 kelvins temperature. Pressure is also applied. And here generally acid catalyst like H3PO4 is used. And this would result into, one side getting H. So any one side gets H. So it's something like this happening. You can always put in like this. So, you have one side getting, H, and the other side getting COOH, something like this happening. And you have CH3 and then CH2 and then COOH, right? So this is what happens. Generally, if you take an unsymmetrical alkene for a similar reaction, once again addition of H and COOH takes place, but this addition and this is pressure here, and the catalytic amount of H3PO4, and here you generally get there's Markovnikov kind of, the major product is based on Markovnikov, where H gets added onto the carbon having more hydrogens. So you have R, CH, COOH, and then CH3. CH3. So this is what you get. You get R, CH, CH3, and COOH. So one side getting H and the other side getting COOH. So this reaction in general is called Koch reaction and used for preparing carboxylic acids on an industrial scale, right? So that's it. We've finished the preparations of carboxylic acid. So in my next video, I would be starting with chemical properties of carboxylic acids.